Okay, cool. Everyone can see the screen? Is it visible for everyone?
Yeah.
Awesome. Okay, so this week we'll be covering system programming. So normally Scratch is extra content bit. Normally these slides we give as after the assignment 2 as extra content. So it's sort of basically to cover some of the mistakes that we often see in assignment 2 and also just provide sort of tips and tricks based on common things that we see people do wrong in assignment 2. So this semester around, we've decided, okay, it makes more sense if we just do this lecture before assignment 2 is due. So this way you guys can actually get these tips and tricks before you guys actually have to need them. So we've decided to sort of cut these into sort of a week 4 content. And this way you have at least 2 weeks to sort of build on stuff we do here and incorporate them into assignment 2. And also this sort of just covers more, I guess, fundamental or advanced sort of programming aspects too. Okay, so first two are just more common sort of mistakes that we see in the report. So this semester assignment 2 doesn't have a report, but you will have a report for assignment 5. So this is still applicable for your assignment 5. A common thing is we see people don't know how to draw diagrams properly. And we often forget about these diagrams in uni because we think, oh yeah, these aren't that interesting. It's just mainly for reports. And actually that's completely untrue. So for example, if you look at the 18 mega data sheet, you'll see that the 18 mega data sheet is full of diagrams. It's full of block diagrams and schematics and program logic sets that basically it's there to actually help you. Yep, so there's no more report for A2. So if you go through the outline, you won't see a report section, and that means there's no report. Okay, so block diagrams. So block diagrams are mainly to give you a high-level idea of the hardware. So often people get block diagrams very confused with schematics. So for example, these are pin layouts. They're giving you the schematics of the system. They're supposed to help you understand how to connect different hardware components. Block diagrams are not doing that. Block diagrams are for you to understand how the low-level connections of hardware is. So block diagrams are like these. So these are just block diagrams I found off Google. The idea of these block diagrams is they're meant to show you how the high-level components interact with each other. So how these components interact, what kind of data they may or may not pass through. So for example, this tells you basically the inputs and outputs of a system. And this tells you sort of how it's connected in terms of the high-level information that's being passed through. What a block diagram doesn't need to tell you is it doesn't need to tell you the pin allocations. It doesn't need to show you what these hardware pieces look like. These things aren't important because these are more like for schematics and for understanding the internal connections, while block diagrams to understand the whole system. Other common things people seem to get confused with is they put pictures. I don't fully understand why they put pictures of it when we ask a block diagram, but some people interpret block diagrams as just sending a picture. Again, that's not the point of a block diagram. A block diagram should look something like this. And it's fairly standard. So if you look across a lot of the documentation we've provided you, and if you look across any data sheet that you find online, more often than not, they'll always contain a block diagram, and often not, they'll also contain like a flowchart or some kind of program logic sort of schematic or diagram. Flowcharts. Flowcharts, I won't go through this too much, but basically try to keep flowcharts neat and simple. The idea is the flowcharts should really give a reader idea of what your program logic will look like. A lot of times people forget to include symbol conventions. So symbol conventions are probably the most important part of the flowchart because you need to understand how each symbol reflects to your code. So ideally, if I look at your flowchart, I can fully understand your code after that. So ideally, when I look at your flowchart, I can go function by function when I look at your code, and I could see how each function is an interaction in your flowchart, and how each function has a place in your flowchart and has a conditional check or function type or input and output or process. Flowcharts, again, people tend to overcomplex flowcharts and make it so these massive webs of crazy stuff. Flowcharts shouldn't go in multiple directions. So flowcharts shouldn't go in like 50 directions back and forth. Every flowchart should have a very clear start and end. Also, another problem is we find that people do too simple of a flowchart. Some flowcharts people do is they just do one block and that block is just programmed. So again, it might seem silly, but believe it or not, people actually have submitted stuff like this. and they just go start system, finish system, and then that's it. And that that defeats the purpose of flowchart. So the flowchart's it's not meant to be either end of the spectrum. You're not meant to provide too much information, nor are you meant to provide too little information. You're meant to provide the appropriate amount. You're meant to figure out how much information does the person need to understand your code, and then how do I depict this into my flowchart for them to understand. So often flowcharts look simple, but the idea is they're meant to be easy to read, and they also meant to provide the correct amount of information. So good idea to always is just to have flowcharts always go in one direction. So the user always knows to read downwards, and only when the arrow points left and right will I read different directions. But overall, it should always go downwards. But I won't go through this too much since more of this is sort of just for you to understand. So let's go through the next parts. Also, just another side note, a lot of these slides do have a lot of information on there. It's because in previous semesters, we sort of use these slides more as we give them to you to read. So these slides are designed to be read, not necessarily presented. So I'm going to more cover the sort of high level aspects of each slide and give you more of the general information. But I do recommend reading through the slides in your own time too, because I'm not going to cover every single word on the slide since there's a lot of content there. Okay, so second part is arrays and data structures. So arrays and data structures are basically, they're not anything unique to mechatronics in a sense, they're just a programming tool. The idea is arrays and data, matrices can basically store multiple variables in multiple values in one variable. And it's something actually very useful. It's something that's very useful for assignment 2. So if you are thinking about how to do certain tasks in assignment 2, you might think about how you can incorporate an array as a data structure in there. So in broad strokes, you really have two types. You have a one-dimensional array. So array will look something like this, int, and then you have x. And then let's say you declare array size 5. So make sure you use these sort of square brackets. And then inside your array, you have value 1, 2, 3, 4, 5. So that's sort of like a one-dimensional array. So if what that looks like is that basically looks like a sort of grouping of values, essentially. So essentially that'll just look like 1, 2, 3, 4, 5. That's basically what your data set will look like. And then let's say you want to store something else. Let's say I want to take this value here, and then I want to take the new incoming value, which is a 6. What happens is I can just go x1, and then I can just do equals 6. And then what that does is this replaces this and replaces it with 6. So the idea of this is basically makes your life a lot easier because you can store multiple values in one. If you were to program this the other way, you would have to program 6 or 5 different variables. So instead of using an array, I would have to do sort of like a x1 equals this, x2 equals this, x3 equals this, and then x4, etc., etc. So that's fairly, in terms of memory, it's not technically inefficient because it's the same as using an array. But the benefit of array is that you can make it any size you want. You can redefine an array as you want. The other benefit is that conceptually it makes more sense because if you start off with multiple variables, you end up have to use 6 lines of code when you use one that can do the same thing. So it's not necessarily more efficient in terms of memory, but it does make your life a lot easier. And often if you use arrays incorrectly, it might be inefficient. And then the other concept is then if you take arrays and then put arrays on top of arrays, you can actually make something we call a matrix or multi-dimensional array. So basically, if you have multiple arrays, so array 1, array 2, you can basically do sort of like what we call a multi-dimensional array or matrix, where you store values on top of each other. And the way you reference that is similar to how you reference an array. You just have 2 square brackets instead of 1. So one would indicate the row and the other would indicate the column. array 0 into, yeah. Oh, sorry. So someone did ask a question about how to reference the arrays. So for example, if I had, again, if we go back to this example of int x5, 5 declares the size of array. So for example, there's a very common problem we call memory overflow. Memory overflow is when we write something bigger or we reference something bigger than the array. So memory overflow is, for example, if I go x6, what happens is this will cause a memory overflow, and often this causes unstable behavior. So sometimes it'll crash, but sometimes in other cases of memory overflow, you will just get a bunch of trash printed out onto your system. So for example, if you see an LCD printing out a bunch of symbols, it'll be that. But for example, if I want to reference this first number here, what would I put into this value? So let's say I want to replace this first number with 100. What do I put into the value of the array? 0, yeah. So what you need to remember here is that every array starts with 0. So the value here will be 0, 1, 2, 3, 4. It's a very common, it seems to be a very common mistake, and don't get me wrong, I make it too. Because, for example, MATLAB often doesn't do this anymore, and other languages often don't start with 0. But with C and C++ and most C variants, you'll always start with 0 at the first value. So if you want to do 0, then that's actually right into the first value. Likewise, this value here would be x4. So it seems to be a very common mistake that I see people, they either, for example, they want an array size of 5, they declare 4 here, and they put that here. And then what happens is when they're calling for the 5th value, so when they call x4 here, they get a memory overflow. Likewise, again, some people, they write 5 here, and then they call they would call x5 instead of x4, and then they would also then get a memory overflow. Because if they call x5, they'll be calling the 5th value, which is outside of the array. So again, these are just small things that you should sort of notice when you program. And once you get a hang of using arrays, they'll prove a lot more useful in your assignments. Likewise, and matrix code is just having an extra sort of designation there where you have a column and a row, while arrays are basically a single dimension. So arrays only really have, you can denote the column. So this number here denotes basically how many columns you have, and then you reference by the column. With matrices, you have a number to reference the columns, and then you have a number to reference the rows. So you can have multiple rows onto one matrices. Matrices are often very useful for later in stuff like maps and things like that you need to do. So for example, a lot of the maps will be done in a binary matrix. So you can use a matrices to do your maps, and you can have other values. For example, let's say I want to do a map, then my map could look like something like this. So, yeah, so this is the exit point, and then these ones are wars. So for example, if let's say I want to do if I want to do a sort of navigation problem, what you can do is you can start thinking about, okay, how do I use a matrix to designate myself? So what you can do is, for example, you can give yourself a value. I can call myself a 2. And then you can think about, okay, so let's say if my robot walks up, my robot travels this way, then how do I do that in code? So in your code, maybe you can have a function for forward. And then forward will always mean, so when you go up, that would always mean your Y value or your row would go up. Oops. Yeah, so you can do row plus plus. You can go, you can even just do like set a number. So if you want to set a number, but yeah, row plus plus is fine. So Y value plus plus. And then you want to reset old value. So what that will do is I'll change this to 2, and that'll change this to 1. What's something else that you can do if, for example, you want your robot to backtrace? So you want your robot to go backwards on your navigation path. So let's say, for example, your robot traveled backwards here outside, but now you want to return back to your starting position. What's one way, instead of changing it to 0, what's one way you can sort of backtrace it? Any suggestions? Well, I guess I'll leave this for you guys to think about in assignment 3 then. You can sort of think about, rather than changing numbers to 0, you can input some more I guess sort of values in there that can reflect into whatever navigation strategy you use. But you guys can sort of think about this more for assignment 3 and 4, because that probably may or may not pop up there. Yeah, so you can do something like that. You can put numbers like 3 or something for that to follow. Again, we'll go through this probably. We'll cover more of these sort of strategies later on. But this will be a starting point for you guys to think about for later assignments. Yep. So placing a 3, valid strategy. There are more sort of, I guess, other strategies you can think about too. All good. So this is just to give you an idea of how to use arrays. One example could be just using arrays to make your code a bit more efficient. So for example, with this structure, if I want to toggle 3 LEDs, I would have to do 3 LEDs manually. So each LED has to be toggled line by line. So I have to have 6 lines for it. While, for example, in this code, I can do that in 3 lines. Because basically what happened is I'm now just using an array to store the 3 LEDs ports or pin numbers, and just having an index counter to basically toggle these one by one. Again, like if you look at the structures here, the structure isn't necessarily more efficient in terms of having the memory. So this takes exactly the same amount of memory, but the efficiency is not really that. But the efficiency is more about easier to understand. You take less lines of code, and you're not basically spamming 50 lines of code when the person's looking at it. So when I read this, I go, okay, this makes more sense because I can see what's being stored in your arrays and what's being happened there. While line by line, it tends to be just, you're gonna have like 2,000 lines of code, and it's gonna be a lot more confusing because I'm trying to navigate through 2,000 lines. And here's just another example on how to store and check values. So I recommend you guys go through that. So now that we've sort of understood arrays or looked through arrays, what do you guys think are some examples you can use arrays in assignment 2, or use a matrix in assignment 2? Since your assignment 2 is in 2 weeks, so it's a good idea to start thinking about how you can use this. Do you guys want to suggest some ideas for your class? Yep, for menus. So menus are a good idea for using. Step and motor position. Yeah, so for example, you can do it for menus. You can do like, you can have a cursor position for menus, and then this saves you from reprinting it a lot. I think probably a password in my mind will probably make the most sense in terms of using the arrays, but menus completely fine. You can use the menus, so you can have
Avi, we can't hear.
There we go. Can you guys hear me again?
Yeah.
Sweet. Sorry about that. So yeah, so menu was a good option. Basically, you can do cursor position. You can go cursor position 0. You can go cursor position 3, and then you can go cursor position 4, or let's say that should be, let's say this was like 6 letters or something, or 3 letters. Let's say cursor position 6, 9, and 12. And then you have a variable for current selected. So for example, your current select could be 0, and that means your current selected option is 0. So whenever your current selected option is 0, you'll be blinking that sort of cell or blinking that area or that word. And then what happens is, for example, you can do, if you want to blink it, you can just do LCD print. And then you can either blink current one, blink, or just, you can do like a clear option. So you can do like clear, just blinking a blank or something like that. But the idea is you can then use the sort of cursor option to control which one's selected. So for example, if I move left, moving left will, strange. Okay. For example, moving left will change my, if I want to hit left button, left, then current select equals 4, and then right, current select plus plus sort of thing. So equals 0 to 4 again. So that's sort of one way you can use it, simply using it for menus. Oh yeah, so you can use it for the stepper motor pins. That's actually a good idea too. So you can do stepper matrix. And then you can store 0, 0, 0, 0, 0, 0, 0, 1, and then put sort of like each zeros in. So and the next one's 1, 1, next one is 0, 1, 0, etc., etc. So you can do that for your stepper motors. And then passwords. So passwords probably the closest one I think for assignment 2. It'll be probably the most useful because you can technically do the other things with logic, but the password really makes a lot of sense if you use arrays. So does anyone remember what the password was for assignment 2? It was so left, right, up, up. Left, left, up, right. Okay, so and then select. So we will treat the select as outside the password. So the first thing you should think about is how do you make left, left, up, right into a password? How do you guys store that? Because obviously I can't store arrow movements or stuff like that into an array. So let's say I have a check. So how would you store this sort of left, left, up, right into a password? So I mean, so this is outside registering. Just how do you store it? So, yep. So you could use the ADC values. That's one option. So I could store this as ADC values and check it. But what's a simpler way I can store this? So think about, if I was to make an array to always check against. So check password equals 4. Yep, you can store as a character. So you can store as either, for example, you can go character and then you store as a L, U, right? That's one way. You can also just store it as a number. So I can also just say every left is a 1, every up is a 2, every right is a 3, and then down is a 4. So then I can go 1, 1, 2, 3. And that's another way I can do it. So this way I now have an array that I can always check against. So this is one array. So this is to always check against this. You'll always go back to check this array. Okay, so now what you need to do is you just need to have an array that stores the memory. So you want to store always the previous 3 values and the current value. So you can have what we call just a memory array. And then this needs to store previous values. So how many previous values do I need to store to check the password? 3, yeah. So let's say this will be the size of 4, so the same size as check password. So memory 0 would always equal a current value. And then memory 1 to 3 would equal previous 3. So this is sort of a simple way to do it. And then what you need to do is every time a new value comes through. So for example, if I have, this is P, let's just say this is P0, P1, P2, P3. And then let's say this was already filled up with, let's say, computer really be lagging today. Let's say this is now 1120. Every time a new coming value comes in, so every time a new value, so let's say the new value is a 1, every time this comes in, all your other values would have to move down by 1. And then the 0 comes out. And then what happens is every time the person press select, you then compare these two functions together. So select would basically compare these two together. So you'll compare the two arrays. With the arrays, you can use functions to check it. So you can use, some people suggest a string comp of a character array. That's one way you can check it. You can also just make your own function to check it. So you can have a number array checker. There's a few options you can do. So I won't go through too many options with that. I'd recommend what you guys should do is look up the string libraries and look up the libraries on. So there are a few libraries, well, in the C standard libraries, you can, there's a function called string comp that checks basically, that compares the two strings or string of arrays with each other, or two character arrays with each other. There are a few other ones like string and things like that that do similar things, but slightly different. I'd recommend going through those and looking at how to compare the two arrays. Also, personally, I do like also just making my own function for it. So you can just use a while loop to check your arrays. That's also another perfectly valid option. So another option I would also bring up here is something we call a circular array. Does anyone have it? Has anyone used it and want to give us like a 2-second brief on it? Or otherwise I just go for it. Anyone have experience with circular arrays? Okay, so circular arrays are basically doing this memory problem a bit more efficiently. So for example, the previous method I showed you there was you have to, every time a new value comes in, you have to manually go through every element and push that element back. So the problem is that's inefficient in the code because every time you have a new value, you basically have to trigger a while loop that pushes every value back. Yep, so it's basically an array with a moving reference. So what circular array does is, if we abstract looked at a circle, I can't draw circles. What happens is, internally, this is 0, 1, 2, 3. Oop, my 3 looks ugly. So this is roughly what this array will look like. In actuality, obviously, this array is still just a block, but let's just pretend it's a circle. What happens is you always have a value called index. This index would always be the starting position where you're writing from. So every time you read the value, you would always read from index as the starting position and the value behind index as the end position. So for example, if, or let's just do a switch case, switch index. So when index equals 0, end position would equal 3. Index equals 1, end would equal 0, and then start equals 1, obviously. 2, end would equal 1, and then 3, e equals 2. So that's sort of how you read it. So for example, if I want to read the memory array check against, what I do is I'll use the index as a start, and then start reading it element by element, and then read the last element, which is the end, as the final element. So this will be whenever you unpack it. So let's say now, so the purpose of a circular array is basically, instead of moving everything back, you're just changing the way you're looking at the array. So let's say the person inputted a 1. That 1 looks at the index and goes, okay, my current element is index is 0. So this 1 then goes to here. So this becomes a 1, and then index plus plus. So then index becomes 1, essentially. So now index equals 1. And then let's say another value comes in that's 2. It looks at index. It goes, okay, I need to move this into 2. Move this into index 1 now. So this moves here, and then likewise, if you have a 3 and then you have a 1, that moves there. So now the problem is, okay, now how do I go back? So at this point here, I want to do index equals 0. So now when index equals 3, index moves back to 0. And then what happens is if I have another incoming value called, let's say 3, it will look back at index equals 0, and then it will overwrite this to 3. So what this effectively does is the end position will always be the second most recent, while the sort of, I guess the previous position will always be the second most recent. And then you always know that when you read this, you can always see that there's an order of operation you have here. So you can always use, actually, I just realized I made this the wrong way. So end positions actually should be 1, 2, 3, and then 0. But basically, whenever I'm trying to read something, I can always use the index position as the starting position here, and then read it in the direction it's saved. So if I'm saving it clockwise, then I should read it counterclockwise. If I'm saving it counterclockwise, then I should read it clockwise. But the idea is that using the circular array, you can always take a new value coming in, and you don't have to shift the whole array left or right. You can just change the point of index that you're looking at. So for example, for your password, you can think about having a value called array called circular array, and then just have a moving index that keeps checking for the current value and then overwrites the oldest value. So for example, in this 3 overwrites 1, the 1 was the oldest value in the circular array. So then when index equals 0, I'm just overwriting that back. Again, this is just another good way to think about how to do programming with the password. Often in passwords, people do use stuff like state machines, which isn't inherently wrong, but in terms of abstract, when you're trying to read it through abstract context, looking at the pass values would actually be a lot more easier to understand, and also make your programming a lot more efficient in the sense that you can just basically be checking arrays rather than incrementing a value based on a bunch of if and else conditions. So this way you're avoiding using a bunch of if conditions, and you're just using an array to store your values. So I'll leave this part for you guys to think about in terms of how to program for your assignment 2. The next thing we'll go through is interrupts. So interrupts are something that we sort of already know that some of you guys are very familiar with, while some aren't. There's something that is very useful for programming and will be very useful for assignment 2. So I know some of you guys already asked questions about it, but I'll just give you guys a general explanation again about interrupts, even though some of you may know about it already. But in case you didn't, so interrupts are basically a hardware, or what we call a hardware signaling. Basically, they're used for hardware components to signal back to the processor about a certain event. So about a certain change or about something that's happened. So if we look at, for example, this block diagram of the Arduino, basically what interrupts are is if you configure certain hardware pieces like the I/O ports, each line here on the data bus, there's an interrupt line. And the idea is you can configure the I/O port to always signal if reset is pressed. So you can tell this I/O port to always signal me if the reset is pressed. So if, for example, the person pushes down on the reset button, this will always send a reset command straight up to the AVR CPU. The benefit of this is the idea is this gives the CPU immediate context over the hardware change. So in a normal operation, the CPU will go through lines of code. So it'll go through line by line. And what happens is the CPU will always signal to the component, and then the component returns information. So a normal communication is the CPU goes, I/O port, tell me what's being said and what's not being said. And then the I/O port replies information back. So the CPU would always provide direct communication. The CPU will go, okay, ADC module, provide me the ADC information. And then the ADC will signal back ADC values. Traditionally, that's always how a CPU operates. Except the problem is, if you do that, you always have an issue with, if you want something done immediately, if, for example, the person presses a reset button, I need to know immediately the reset button is pressed. So then you need to give a hardware component some way of telling the CPU, okay, something has happened. You need to know this immediately, or the CPU needs to do something about it immediately. But the CPU also has to have a way to respond to that. So the CPU has to know exactly how to handle an interrupt. So this is why interrupts need to be properly set up, because the CPU has to design a way that's safe to handle interrupts and that's safe to receive interrupts. So what happens is you need to set up interrupt correctly, and then you need to designate how a CPU is meant to behave when you have interrupt. So there's something we call interrupt vector table. So each vector is handling a certain signaling from a hardware component. So for example, you guys probably have used the timer interrupts already. Each timer interrupt will signal a different message from hardware to indicate something has happened. Most cases, either a comparison has happened or overflow has happened. But for example, timer 1 also has a capture module that captures when basically captures when another timing has happened in terms of the checking the capture module sort of thing. Other things will be ADC changes when ADC conversion complete. You can possibly do it. There's also other serial interrupts and whatnot. But the idea of the interrupts is that they provide your hardware ability to immediately tell the CPU something's happened. So you probably want to be careful of this often. So often interrupts can get a lot more confusing when you don't properly configure it. So this is why you do have to read through the documentation for the interrupts a lot. Another thing to note is that this interrupt table also gives you the priority of the interrupts. So reset will always be the highest priority. So what this means is that if reset button is pressed, it doesn't matter whatever else is happening in your system. It could be doing another interrupt. It could be doing any operation. The reset button will always reset the system. Likewise, for example, if a timer 2 compare match A happened, then a timer 2 B match would not ever happen. A timer 2 B match would just never happen because the A match is currently, if you're currently in the interrupt function for that, it will never allow something of lower priority to interrupt over a high priority. So I've given you guys a basic example of how interrupts should look like. But essentially, you always have to remember to set this up correctly. So always set up your interrupt to the interrupt you want. So in this case, I set up the timer overflow. So every time the timer goes from 0 to 255, it will signal the CPU that an overflow has happened. And what happens is the CPU, whatever line of code it's happening here, it'll always jump back to the interrupt and check the interrupt. And once the interrupt's done, it'll go back to whichever line of code it was at before. So the idea is whatever's happening in your CPU will pause whatever it's doing and go to the interrupt. So these are some common mistakes that I see in the assignment 2 that people always do. Some of the mistakes are quite silly. For example, some people basically have interrupt set up, but the interrupt doesn't work. That's also very common. Some people just set it up. Basically, they try it, the interrupt stops working. They go, how come? And then they just give up on the interrupt, but they keep the interrupt code there. A very, very common problem, people just don't declare global interrupts. They don't set global interrupts on. So if the global interrupts is not set on, the CPU would ignore every interrupt signal that's happening or every interrupt vector. It wouldn't even basically receive anything. It's only when you set global interrupts or you enable global interrupts, that's when the CPU knows there's interrupts coming in. So because interrupts are very common to causing unstable behavior if not done properly. So that's why the CPU has a lot more safe bars, or there's a lot more configuration safety standards that you need to implement before you use the interrupt. And one of it is that setting your global interrupt there. The other one is you need to configure the hardware to properly send interrupt vectors or send whichever interrupt you're looking for back to the CPU. And then you need to have a line of code that tells the CPU what to do when you receive the interrupt. So another problem is declaring variables volatile. Often people forget that variables that interact with the interrupt signal need to be declared volatile. So for example, your milliseconds here, you need to declare this milliseconds volatile. Oh, okay, interesting. So you need to declare volatile because milliseconds is being changed by this interrupt vector here. My computer spasm. But yeah, so the idea is the variables that are being changed rapidly by interrupt are also being changed unpredictably. So what happens is your CPU is going to have to be accessing your RAM at a very rapid pace to change, or at a very unstable, unknown pace to change its variable. So if you declare a volatile, it means that your CPU, or it means that beforehand in memory, it's stored as a volatile. So it's stored knowing that it's going to be rapidly changed. I'll go through why this will be a bit more important when you understand memory, and you sort of understand why it's important to declare something volatile later. The second thing is ISRs are meant to be fast. You're always meant to have the minimal line of code in ISR. So for example, in this function I've given you here, this is about how much you should have in the ISR. Your interrupt should basically only have 1 or 2 lines doing very simple operations. The reason why is because the longer your ISR takes, the slower your system is. And not only that, the longer your ISR takes, it also interrupts with other ISRs. So if you have another interrupt signal firing that's supposed to be happening in the next millisecond, what happens is if your interrupt is too long, it will be stopping other interrupts of lower priority to fire. So you'll be missing stuff like other timing increments. You'll be missing ADC conversions and whatnot. So you might be missing another event that's happening. Another thing people do is they often use more than one ISR. That's not necessarily good or bad, but often using more than one ISR means that you have to have a really good understanding of the interrupt firing system. You have to understand which interrupts you're using, and you have to make sure your interrupts don't interrupt each other. For example, a very common one is people use, for example, timer 1. So people use timer 1. They fire it every 1 millisecond. And then timer 2, they fire it every 2 milliseconds. The problem is often timer 1 would always fire at the same time as timer 2 every 1 millisecond. This is just the example. I don't have any reason. I just pulled timer 1 out of thin air. But the idea is basically every time timer 2 fires on the second one, every time timer 1 fires on the second millisecond, it will basically be firing at the same time as timer 2. So now if we look at the priority table, timer 2 is always higher priority than timer 1. So if timer 2 and timer 1 both fire at the same time, then what happens is timer 2 will be firing at a higher priority, and it will ignore the second millisecond of timer 1. So what that means is often timer 1 is not going to be accurate to the millisecond. You're going to be either losing milliseconds or having a cumulative error to it. So your timer 1 will always be having the wrong timing. And that's a problem. So if your system depends on timer 1 for precise timing, you're basically going to inherently have an off timing in timer 1. And the worst part of it is because if you don't realize this is happening, you're depending on basically an unstable timer. And this is going to basically make your system a lot more inefficient, but it also make your system a lot more unstable. So it's not necessarily wrong to do 2 timers, but again, you have to think about how best to implement 2 timings without having them interfere with each other. You want to make sure they're both firing in parallel and not interfering and never really firing at the same time. So this is something that you guys have to do when you're thinking about programming. But what I recommend is always just use one interrupt. Because for example, if timer 1 is doing 1 millisecond, timer 2 is doing 2, why not just have a counter variable that counts? Yeah, just counts 2 ms and just check timer 1. So that's sort of the way I recommend it. Always just pick the fastest, like if you have 2 timers, just pick the fastest timer and then just count how many times that timer runs. So, if 1 millisecond has passed, then just do this. If 2 milliseconds has passed, do that sort of thing. But always remember, don't do it in the interrupt, do it outside the interrupt. So all the interrupt should be doing again is just incrementing a variable. Every other operation should be handled outside the interrupt. So just, again, this is more information to cover for multiple interrupts, but I'll let you guys read through this in your own time. Some useful documentation. So again, the datasheet is great for it. I found some really cool forums. So these things are just things people have written for interrupts and how to better understand them. Basically, they're like open letters or open articles for people to read. So I'd recommend going for those. I found those very useful just to understand the interrupt system better. And hopefully you guys can find that useful for understanding interrupt systems. Okay. So the final part of this class will be looking at real-time operating systems. So real-time operating systems, the name sort of sounds like a real system, but it's actually more a design philosophy. So real-time operating systems or it's more like a design standard. So it's a standard convention for how to design a system. Don't treat what I say here as the everything about RTOS. There's actually basically a lot of content and a lot of designs for RTOS systems. So for example, if you Google a list of real-time operating system designs or models, you'll find probably over 100 models based on multiple pieces of hardware, based off multiple designs, efficiencies, stuff like that for multiple purposes. I'll be covering more of the basics and more of the fundamentals, so the absolute tip of the iceberg to help you get into that entry level of understanding. But there's actually a lot that goes behind this, and there's a lot of content that I don't include, just so that you guys can first understand the most simple components, and then in your own time, research more about how to make systems more complex, sort of thing. So the base idea of RTO systems is to create real-world systems. So the idea is to create systems that are useful in the real world. For example, in the real world, if you have a device, you probably don't want this device to constantly be crashing, and you don't want this device to constantly be lagging. So the idea of the system is that it minimizes lag or latency between tasks, and it also tries to make your system as stable as possible. So as foolproof as basically can take any user input and never crash. So the idea is your system should always try to avoid crashing and avoid wait time and avoid sort of, you have to be able to perform the tasks you want at this time you need. So again, it's like driving. If your car has if your car has a lag time between inputs, then if you brake, then your brake only happens 2 seconds later. That could be a matter of life and death. That could be a matter of a car crash and not a car crash. So your car, you want your brakes to be immediate. You don't want your brakes to be lagging. Another thing is obviously you don't want your car to be crashing halfway. You don't want your car to stall up and basically break down every 2 seconds. This sort of methodology applies to any system you make. Likewise, if you make a drone, you don't want your drone to be flying at a delay time or a system lag of 2 seconds or 1 second or a few milliseconds. You want your system to be relatively immediate. But then you have to pit these things against the reality that in real life, you can never have a immediate system. You can never have a sort of instantaneous occurrence. Everything will always have a system latency. There will always be a delay time between user input and reaction. But the idea is you want to minimize that. You want to make that the most efficient as possible. So that's why I'm sort of going through some basic ideas of how to make it more efficient. Likewise, for assignment 2, I do hope that you guys can think about how to make your assignment 2 more efficient. Like you don't want your assignment 2 to be constantly crashing, nor do you want your assignment 2 to be lagging every 2 seconds, or I have to wait there for 3 seconds for stepper motor to make a step. So the key things are just stability and timing. If you guys want to break down the 2 key goals, is that you want to have a stable system and a nicely timed system. So to understand real-time operating systems, you need to sort of understand how the terminology or how the abstract idea of tasks are done. So there are 2 words that so you guys have to understand. These are not specific to mechatronics. These are actually used highly in computing too. So there's threads and there's processes. So the idea is threads are basically like a single operation or a single task. And then a process is like a grouping of tasks. So a process can be made up of multiple threads. But the idea is a thread is basically the lowest level of a task. Each thread should have a specific timing. So it has to have sort of like a time that's going to be executed. And it has to have an order of execution. So your thread has to be executed in a specific order. So for example, you see thread 1, after thread 1 is complete, thread 2 is done. And then after thread 2, it goes back to thread 1. But one process can have multiple threads, but a thread can only be done at once. So a thread should have 3 states. It should be either running. So for example, right now a thread's running. Right now a thread's ready. And then there's also waiting. So a thread right now the thread is blocked here. This thread is blocked while thread 2 is done. But then once thread is ready, thread 2 goes to thread 1 back. Threads and processes aren't necessarily something physical or something tangible. they're actually an abstract way of understanding it. But the thing is, the reason why we have it is that we need a standard or standard terminology to use to describe things. Because, for example, a thread could, if we talk about tasks, a task could be anything. You could have a big software program that could be a task, or you can have a low-level thing that could be a task. So what happens is we need a standard to basically name certain operations or name the level of operation. So that's why people have chosen thread and processes as the standard or as the terminology used to name threads as low-level process, and then threads as low-level task, and then processes as a group of threads or a bigger operation that's happening. So you can actually see threads and processes in active computing. So for example, if you look at your task manager, you can actually see your CPU is currently processing certain amount of processes and processing certain amount of threads. So these things are actually very existent in current computing. Likewise, in robotic systems, you also want to think about creating a system that's processing threads and processes. Likewise, for assignment 2, it's a good idea to think about what do you consider threads and what do you consider processes in assignment 2. Again, this is just to better understand the standard terminology. They're not necessarily rules or anything. It's just more like this is the standard people use, or this is the terminology people use. So, for example, you don't want to describe a thread to one person and have him think of something completely different. So the idea is this way, across engineers, you are all on the same page on what a thread and what a process is, and you understand what it is, sort of thing, when you talk to other people or when you program across projects, sort of thing. Okay, so there's two types of processors normally nowadays. There's single core and there's multi-core processors. So for example, you'll see some of your computer processors are multi-core nowadays, or most to all of them are multi-core processors on your PCs. They often have 4 cores, 8 cores, etc. What each core signifies is that your processor can handle multiple threads. So if you have a single core processor, that means your processor can only handle one thread at a time. Well, if you have a multi-core processor, it means that you can handle more threads. So generally, the rule of thumb is obviously more cores is better, but technically speaking, more cores means that you can do multiple threads, but it's also about the efficiency of the multiple threading. So something called hyper-threading means that you can handle multiple threads more efficiently, even though you have the same amount of cores as some other multi-core systems. For example, for our Arduino, is our Arduino a multi-core system or a single-core system? Which one's the Uno? Single, yeah. So the Uno is what we call a single-core system. The reason why is multiple cores will require more power, and often they require they produce more heat. So a single core produces an amount of heat. If you have multiple cores stacked on each other, you produce more heat. So that's why, for example, for your PC, you'll see that you'll need a giant fan, or you need a liquid cooling system, or you need a proper heat sink attached to your core. Well, with the Uno, you don't see someone attaching a fan to the Uno or attaching a giant heat sink to the Uno. Because the Uno only has one core, it doesn't produce as much heat and doesn't require as much power. The problem with the Uno, because it's a single system, is that you can only do one thing at a time. So like what you've been doing now with programming, you kind of realize the challenge is, if you need to check 2 things, you can't check 2 things because you can only process one thread at a time. So your Uno is only able to go line by line and process one operation by operation. If you had a multi-core system, then you can process multiple operations at the same time. So this is sort of where RTOS really comes in. So RTOS can be used for multi-core systems. There's nothing wrong with it. But it's really important in single-core systems because you really need to think about how to do multiple tasks in a timely manner while minimizing stability, while minimizing crashes and minimizing latency. So I've sort of gone through 2 of the general parts of it. So one part is minimizing latency. So with minimizing latency, you have to understand that every instruction, every line of code, every operation takes time. So for example, does anyone know what's the speed the compiler will process each line of your code by? What's the rough frequency or compiler at? So line by line, what's the frequency your CPU roughly go at for your Arduino Uno? Yeah, so it'll go roughly at the speed of the oscillator, so that's 16 megahertz. So that means at minimum, your system will take a 0.1 or 0.2 0.1 something microseconds. So roughly each operation will take a decimal place of a microsecond. But in practice, often each function and each task you do, even like for example, if statement will take at least 3 instruction sets to perform one if statement. So in reality is that even your most basic functions will take multiple instructions to do, and that will mean it takes time. So you can't think of programming as instantaneous. Everything takes time. So the idea is you want to think about if you have certain tasks, you want to be able to minimize the waiting time between tasks. So in practice, what that means is, for example, using a timing-based structure. So using interrupts to basically control the timing of your operations. The other thing is try to minimize things like while loops and minimize things like while waiting. So waiting for certain operations to happen. Rather than waiting, you should have a timing structure to prompt certain things to happen instead. So for example, using sort of the interrupt vector, you can do sort of like this if structure. So this if structure, basically, if your certain time hasn't passed, it will move to the next operation rather than having to wait here for the operation to complete. So stuff like this is basically stuff you can do to try to improve your system structure to minimize the wait time between operations. So this is sort of more, I guess, abstract for you to think about, but you can also start thinking about, if you go line by line in your code, basically try to think about, okay, where's my system getting caught up? What places is my system waiting for a certain operation to happen? And how can I make this more efficient? The second thing to think about is memory. So a very common thing that causes systems to crash is not having efficient memory or not having efficient memory sharing. So that's why it's a good idea to understand memory. So this is a diagram of your SRAM. Does anyone know how big the SRAM for the 80 mega is? So what's the size of the SRAM? Yep, 2,000 kilobytes. So 2 KB. Okay, so what you need to understand is whenever you store something in memory, every variable you declare is stored in memory. So for example, you have global variables here. And then you have local variables here. So this is local variable. But what often people forget is not only local variables and global variables are stored. For example, stuff like this is what you call undeclared variables or undefined variables. Oh no, well, it's defined, so it's just undeclared. These are also stored in memory. Okay, so just as a quick task, where do you guys think these three are stored? Which parts of memory are these three stored? So you have 3 parts of memory. You have stack, heap, and static. So where is global stored, where is undeclared stored, and where is local memories or local variables stored? So these are local declared variables. Where in memory are these stored?
Harvey, we can't hear.
You can't hear?
Yeah, that's okay now. Yeah, thanks.
Okay. Oh no, I'm just asking a question. So do you guys, anyone got any ideas where these stored? So all your variables are stored in SRAM. Can you guys hear me? Yep, so all your variables are stored in SRAM. These are good guesses, but so the way you have to look at it is that you can look at the naming of the data too. So static is data that is always permanently stored in memory. So these are data that basically are gonna have to persist across functions. So whatever functions are occurring, static data will always be there. Heap are data that are dynamically allocated. So they are data that are allocated through, like, for example, malloc or pointers. So they're often data that's allocated in memory allocating pointers and whatnot. So therefore, if you declare a pointer, these are stored in the heap. So for example, if I do like something like pointer star int, that's stored into heap memory. Your stack memory handles whatever memory that's sort of being implemented just in the function. So this is inside the function. Oop, that's not visible. So the idea of a stack memory is that the stack memory is changing. That's why the stack memory is at the top side. So there's actually a reason why stack memory is up here, while these memories are down there. So the idea is the bottom side should always minimize changing. It shouldn't be changing that much. While the top side, the stack memory, should be always either going up or going down. So what happens is when you're inside the function, your stack memory will take every local variable. So your local and your undeclared variables will be stored in your stack memory, while your global memory will go into your static. So the reason why your global goes into your static is that technically you shouldn't be declaring more global variables, or you shouldn't be increasing the size of a global variable once you've declared it. A global variable is sort of in the name. It's meant to be global. It's meant to be minimized changing or minimized size changing. So this is sort of why you shouldn't really store arrays as a global variable. You should store arrays as stack. The other benefit of stack is, so stack is allocated and deallocated based on function. So for example, if I'm in setup, these will get stored into stack memory. But once I finish setup and once I'm in the main loop, these memories get deallocated. So what happens is that whatever is declared or undeclared, your stack memory would always deallocate and reallocate based on local and global, based on the function you're in. So if you're in a certain function, let's say do this. So let's say I have a function called do this. And then this function declares int x equals 0. What happens is when I enter this function, this is my stack, x goes into it. But then once I go out of this function back to my loop, so once I get to this step here, x gets cleared again. So this gets deallocated, and then this clear memory. So it deallocates whatever's being stored in the variable and then goes back to whatever. So stack's always changing. Your stack memory is always changing. So why do you think it's often more efficient to declare things as local variables rather than declaring it as a global variable? What's more efficient about local variables? Yeah, it saves memory, right? So for example, a lot of things you do in your system, you don't actually need to be declaring as global. I see a lot of people in their assignment too, they declare certain things as global when they don't need to. It's just, you don't need to constantly know this variable here. So it actually saves a lot of memory if you declare as a local variable instead. Because if you put as local variable, you are currently allocating and deallocating this memory. Another problem is there's something we call fragmentation. So what fragmentation is when you're inefficiently using undeclared variables. So what this means is, for example, right now, if you look at the setup function, the setup function, how many zeros does it have? So it has 3 zeros here. So this is the same value. These zeros are the same value. How many times in memory is this 0 stored? So how many times in stack memory is this 0 occur? Anyone know how many times in memory this is stored as? Yeah, it's stored 3 times. So that means it's actually taking 3 integers, or around 12 bytes. Well, it's about 6 to 12 bytes essentially. So this is stored 3 times, even though it's the same number. So let's say if I instead had a global variable for this number, then it will be stored only once, because I'm only having this one global variable, or even just having a local variable that's called 0 and then storing that once. Basically, or even just having a variable for your cursors, having x and y, then this means that I'm not declaring a bunch of numbers into my memory. I'm only declaring x and y once, and then that's being stored. This is a common problem with what we call magic numbers. So what magic numbers are is that they're undeclared numbers that are basically you're putting it in your code that's so just magically there. So like dance 0 is a magic number. What you should be doing is you should be declaring a variable for it, and then you should be changing that variable depending on what you need for the code. So this means that you're actually not saving the same variable or saving the same magic number in your code multiple times, and you're only using one variable, the one memory space to access it. So this is just things that you can make your memory more efficient. Because the problem is if you have too much going on in your memory, you have something we call memory overflow. So that's when your stack and when your heap memory creeps up onto each other and then collides in this section. And what happens then is often your system will either crash, but often, more often not, your system will actually become unstable. So when you have memory overflow, what happens is your system has a very high chance that it's going to start spewing random signals, and it's also going to start writing to random registers and doing random behaviors. A very common thing, this actually happened in self-driving cars once. I believe a few years back, there was a memory overflow issue that caused caused the car to crash, essentially, because the car basically the programmer basically didn't implement a optimized memory, and the car basically went crazy and then swerved out and crashed onto the side of the road. So these things, again, do have real-world impacts. It's about understanding how to better make it more efficient so that you avoid these sort of instabilities and avoid these issues in the real world. So that's why it's a good place to start to learn about this now and start to think about how you can implement it in assignment 2. Okay, so another thing to think about is just memory sharing. So we've sort of already covered through why not to do global variables, but you also want to think about is how to efficiently pass variables between each other. What a lot of people do is they declare a lot of global variables. So they do like global variables. So maybe they do int x and they do function one. Function one, they just do it empty and that uses int x. So that uses x, and then function two uses x again. So what happens is often or not, when you do something like this, when you have one global variable and you have multiple functions affecting the global variable, I feel like probably if you look at your code, you'll see this happen a lot. And I can guarantee probably at least 70 or up to 100% of you guys are doing this, where you have one global variable being interacted by multiple functions. This is what we call memory sharing. So this is what happens when you're sharing the same variable between two functions. Inherently, this is not wrong. Yeah, this is something I do too. No, it's not necessarily wrong. But the problem is this does make your system less stable because this means that the state of X, you're not too sure what's the state of X right now because the state of X is currently changing between function one and function two. So because currently if you want to know where X is, it really depends on what's being called right now and what's happening. So what happens is instead of doing this, what you should do is you have an output X as function one. So instead of declaring X as a sort of input variable, you have an output and then you also have an input as X2. So let's say I make this an integer output and then an integer input. So function one takes in a value and then function one outputs a value. And then function two, likewise, takes in this output. So function two, again, you can just take in this integer output or as an input and then output another value that function one can take back in. So if you do that, one hand is you can avoid using global variables that constantly changing. And the other hand is you always know what the variable state is going in. So you know that whatever's going into function one is the output of function two. And you always know that whatever's going into function two is the output of function one. So this means that as a programmer, you would always know the state of the variable before you go into a function. While if you do as a global function that's constantly being changed within the function, within a function space, you don't know the state of the variable. The state of the variable could be something, whatever the system's in right now. So obviously with two functions, it seems quite simple, but now imagine in your assignment 2, you have 6 functions that's using the same global variable. Then the state of that global variable becomes very tangential or very unpredictable because you don't know. It really depends on what's happening in your system, and you maybe if you had incorrect line of code that's changing the wrong variable, then your system could be in an unpredictable state. So if you, instead of using global variables, use local variables to store certain things, and you pass these local variables within each function, what happens is you're making your system more stable, because your system now, you as a programmer know whatever data is coming in is a reaction of another function. So this just basically gives you more control over your functions. Again, we've sort of covered through the global variables and why that's not efficient, so I won't go through that again. But these are just things that you can think about when you're looking at your assignment 2. So again, if you go through your assignment 2, I recommend looking at your code and seeing where you can make the memory more efficient. And always try to use your functions as inputs and outputs rather than doing void. So a lot of people just do void and just have a void input, void output, and then just use global functions. And that's just not efficient, because your memory is going to constantly be used and it's going to be a lot more unpredictable. Okay, so we'll cover the final section of this, is what we call scheduling. So I'll give you, basically, these are the free models that often people use, but these models are very basic. So these are the basic models people use. And these to get you start to think about how would you model your assignment 2 for scheduling. So just a basic definition of scheduling is designed as it's designed as a methodology to control the flow of your program. So the scheduler basically controls what operations are happening when. So they're designed to basically make your system more efficient, and also designed to, well, actually, no. So they're not designed to make your system more efficient. You design the scheduler to control the flow of your program. That's probably a better definition. That as a programmer, you're the one that's programming a scheduler that will control how to best handle each operation of your program, and how to do it in a manner that's stable and that's time efficient, that you minimize the latency between operations. So I've outlined some schedulers for you to look at, and we'll sort of go through each of them. So inherently speaking, most of you guys will program in a scheduler already. So the way you control assignment 2 is you have to program a scheduler to handle everything. So without even learning RTOS, you guys are already performing this. You guys are already doing this in your code. The reason why I show you these is not that saying you're not doing this, because you are doing this, but I want you guys to do it in a way that's more efficient, or that's more according to an industrial standard, or that you guys, it makes more sense to you guys, and you guys are thinking about this more as an actual real-time system, rather than thinking about this as just programming sort of thing. So this is why you guys want to think about, for example, if you're programming a system, you want to think about what kind of scheduling am I using? Am I using a time variant, or am I using a cooperative scheduling? So I'd say most of you guys are probably using a time variant one, but we'll go through cooperative scheduling too. So cooperative scheduling is basically a system where all your tasks are cooperating with each other. So what that means is that you have a set order of operations, and that your tasks are prompting each other to begin. So I'll go through this diagram instead, just to make it more sense. So for example, imagine you have 3 tasks. So let's say this task is just timer. So timer count. This task is your motor. And this task is checking sensors. What cooperative scheduling means is that every task has equal priority. So every task is equally important, and your system needs to perform each task in order. So the order will always, let's say, be task 1, then task 2, then task 3, then task 2. And then your system will go back to task 1. So for example, what that would look like maybe is you have a loop, you have a void loop, and then you have state. Or no, you have an integer, global integer called state. And then you guys will have a switch case. And then in this switch case will be your state, and then task 1, task 2, task 3. Task 1, task 2, etc. So you have a switch case that controls task 1, task 2. So this is the most basic way to look at scheduling, is essentially what's happening is after each task has happened, each task will then output the current next state and signal for the state complete. So what happens is each task has a ready, Each task can be ready, it can be running, or it can be blocked. So each task will be ready, and once it's ready, it will be in a queue. So if it's ready, it'll move. If it's not ready, it'll be skipped. And then each task will be running. So the running is the current task operating. And then the block is basically saying that my task is now waiting on the queue. So my task is blocked for the next operation to occur. So in a basic term, cooperative scheduling is just every task has to be done in a cycle. So your CPU is basically just doing task 1, task 2, or task 1, task 3, and then task 2, and then it goes back to task 1. So it's just doing it one by one, and it's just doing it by switching. So between each tasks, you have to make sure that there's minimal latency. So each time you have a switch here, you have to make sure that this is very done very fast and very minimal wait between time and between the two. So what this means is that you have to make sure that your variable is ready or your value is ready before you switch. So for example, you have a value ready here, then you do a block. So your scheduler will basically block this and then say, okay, but this guy is now ready. So your scheduler will then see he's ready and then perform a switch, and then he goes to running. So this way is basically purely just one after the other. After one task completes, it will do the next task. After the next task completes, it will do the next one. What do you guys think are some of the problems with cooperative scheduling? For example, when you program assignment 2, why don't you just do one task after the other? Any suggestions? Yep, so you might need to do multiple things at once at a speedy pace. So, the idea is you don't want to wait till your motor does one revolution before you check the sensors, because you may want to check the sensors faster. So that could be one thing. Is there any other suggestions? So one way you can do multiple things is you just make this shorter. So instead of making task 1 do one revolution, you make task 1 do one step. So then after one step, you switch it. So every time you do one step, you switch to checking the sensor. And then every time you get one value, you go back to doing the next operation and next operation. So technically, cooperative can do multiple things. Well, it doesn't do multiple things in one. It has to do one thing at a time. But for cooperative scheduling, you can make each element as small as possible and then just have them run really fast between each other. So that's still possible, but it obviously is not very efficient with running this. Okay, so another problem I'll propose to you guys is that it's not memory. Another problem I'll propose to you guys is cooperative scheduling is bad with timing. So because the problem is you don't have a set time to run each block. Task 1 could take 1 millisecond. Task 2 could take, a arbitrary amount, like maybe, let's say 0.1 microseconds to like 100 milliseconds. Or let's say motor will take 1 microsecond to 100 milliseconds, sort of thing. And check sensors could again take like, 0.1 microsecond. The problem is cooperative scheduling, you don't actually know this. So maybe check sensors could take 2 milliseconds. It depends on whatever settings coming in, and it depends on whatever input variable you have. So cooperative scheduling, your system is not very precise with timing. So for example, if you needed a motor to do something, so for example, I need the motor to immediately do an operation here, but the problem is my system is currently here. That means for cooperative scheduling, I always have to wait for the time to complete. And then I have to wait for the sensor to finish converting. So at maximum, that could take 3 milliseconds before my motor starts moving. So what this means is for cooperative scheduling is simple. It's a simple design. It's very easy to understand. But the problem is it's also, because of the simplicity of design, you can't get precise timings, which you may or may not need for assignment 2. You might want to have a more precise timing for assignment 2, and you can't get that with a cooperative scheduling. But with that said, it's not saying that's bad. So for example, a lot of people can do cooperative scheduling for assignment 2, and you can make it very efficient. So it's possible to make it very efficient, but you need to be aware that, you have this issue where you won't be able to get precise timings with that. So this leads to another design called preemptive scheduling. So a lot of systems use what we call a preemptive scheduler. So what preemptive scheduling means is that it has the ability to signal or change the flow of programming. So cooperative is a single flow. So cooperative is always going to be task 1, T1, T3, T2. That's cooperative. What happens is preemptive, you can have task 1, but then it's meant to be task 2, task 3. But then I can switch this out. I can go, okay, wait, this now needs to go to task 2. And then, so I put task 2 in here, and then task 3 has to move back. So the preemptive scheduler has the ability to basically swap whatever operation you have right now with another operation coming in. So a preemptive scheduler can actually alter the flow of the program. And what this does is this means that if you need something done immediately, your program can do this immediately. So this could be useful for things like user input. So for example, if I press forward and my robot's driving forward, I might suddenly press back or might suddenly press the brake. Then your system doesn't want to get stuck driving forward. It wants to be able to immediately change this operation to driving backwards or stopping or something like that. So you need to be able to suddenly preemptively change the next task to something else. And this is sort of important. So what another quality of preemptive scheduler is that it rather than, so cooperative deals with tasks. Cooperative deals with task 1 equals task 2, then task 3. Preemptive scheduler, what it does is it breaks every task into what we call time slices or time bursts, or some people call it time quantums. Basically what this means is that every task has to take an amount of time, and this time is designated by a standard. So I'll sort of show you what this looks like. So there's two designs with preemptive scheduling that we'll go through. First one is preemptive priority. So what preemptive priority means is that every task will have a priority. So every task will have a priority, and that defines the order of operation. So for example, when you look at this design here, it's the same time task 1, task 2, task 3. But what you see is that task 1 is now 2 slices, task 2 is 3 slices, and task 3 is 1 slice. So if you look at this timeline now, you see that each task is now divided into its own slice of operation. So what happens is the slices define is how long this task will operate and when I can pause this task. So for example, what you see here is that you have a scheduler. So this scheduler here defines what's happening. And this scheduler here can now start intervening with the operation. So initially it will be task 1, task 3, task 2. Task 1 will be highest priority. So if let's say we assign priorities, priority 3 is the highest, priority 2 is the second, priority 1 is the third. What happens is right now it's task 1 is highest priority, task 2 is the second highest, task 1 is the third. And then what happens is, let's say task 3, the interrupt signal has registered something has happened. So this interrupt signal tells the scheduler, I now need to do task 3 again, and task 3 has to be done now. So what happens is the scheduler looks at the task 2 and sees, okay, it's completed 2 out of the 3 time slices. So I'll stop my operation on the second time slice. So this is the first time slice, second time slice. The scheduler will stop this and make task 3 high priority. So task 3 is now highest priority, and then it will go into here and interrupt task 2. So you see how task 3 operates. And then let's say task 2 has started again. Task 2 has now, task 1 has now occurred. So then task 1 becomes highest priority. So then it interrupts, once time 3's time slice has finished, it then interrupts this again and shifts task 3 to, the current task 3 into the next priority along. So what happens is you're basically constantly assigning priority based on the need. So if a higher priority operation comes in, then every other priority gets shifted down, and then something occurs. So then the scheduler pushes it to the next thing, and then it resumes operation as normal. So this goes back to normal operations again. It is a bit hard to abstractly understand, but what this could be is basically, for example, task 3 is robot drive forward. So this is just robot drive. And then task 1 is, let's say, read sensor. And then task 3 is user input. So just user input there. So for example, your robot read sensor, and then the user pressed forward. So forward. And then the robot has to drive forward. So the robot driving forward will take the most time slices. So the robot's currently just driving forward, it's moving forward. And then let's say the user suddenly presses stop. So this is the stop command. Oop. Or let's say this is the left command. Probably let's make it easier. So let's say this is the left command. So the system can either, in a cooperative system, the robot would finish driving forward before it makes a left system. The problem is, let's say in front of the robot's a wall. Then if the user presses left, you want the robot to stop immediately. So that's where this sort of priority system comes in, where it suddenly interrupts this robot's driving and then changes the direction to left. And then suddenly, let's say the robot turns left, and then the sensor suddenly reads a wall that's to the left of it. So the sensor sees a wall. Then the sensor wants to then, you don't want the robot to drive into a wall either. So then the sensor will then signal the scheduler that you need to change the priority, that there's now a wall detected. So then again, this tells the scheduler, okay, I see a wall, and then I want to stop the system. So I want to have a stop command that stops it. And then you go back to the normal operations of read sensor, check user input, and drive the robot. So preemptive scheduling seems to be quite standard. And there's a lot of benefits of preemptive scheduling. So the idea is that the preemptive scheduling means that your system can be more reactive and that your system is being changed based on events. So let's say one event happened, your system can change it based on events. And then when there's no events happening, your system will go back to the regular flow of operations. So it's like cooperative scheduling, but just with an intervention system. The problem with preemptive scheduling is that one key complaint is that it is quite complex. So you do have to have a very good abstract understanding of your system. And you have to really be able to understand how the timing works and how to intervene correctly. So for assignment 2, you might want to think about how to do this and how to best use the interrupt timings for this. But again, these are just things that you can sort of think about that might be useful to implement for this task. This doesn't necessarily say it's suitable, but you can think about how would you do it. Sort of thing. So I'll go through the last one. So the last one's what we call a round robin system. So a round robin system is slightly different from cooperative and preemptive systems. The idea of a round robin is that instead of your programs having a natural flow of operation, so normally the flow of operation should be just preemptive, so co-op and priority. So co-op and priority, naturally your system will always do task 1, task 3, task 2. So priority system lets you intervene. So that lets you intervene between the flow operation. But there's always still a natural flow operation. There should be a flow between task 1, task 3, task 2. What round robin does is instead of having a natural flow of operation, your scheduler inherently controls the flow of operation. So there's no natural flow anymore. Your scheduler is just the function that basically tells your system to go to what function right now. And how it does this, it does this by time. So what this means is every task has to have a arrival time. And what that arrival time is that this is the time that the task has to come in. So this is the time that you need to do this. So this might sound a bit abstract right now, but the way you can think about it is that you have a start system time. So your system starts as 0, 0. Let's say every 1 second, I want to update clock. So I know that every 1 second, so every time the system starts, let's say this is 0, 1, 1, every 0, 0, 1, 0, 0, 0, 1, 2, I know that I need to update clock. So what this means is that the system knows at this time point, I need to always update clock. So the system will have a global clock, and this global clock will basically have a schedule of every time that this thing needs update. So this is the arrival time for the clock would be every 1 second. Well, let's say I have a stepper motor. I know that every millisecond, I need to step once. Then the arrival time for the stepper would be stepper would just be every sort of this millisecond. So what happens is now my scheduler needs to use the global clock to check the current time. So essentially, it's like your scheduler has a watch, and then it has to follow this timing schedule of knowing, okay, currently it's 1 millisecond has passed. I need to be doing this right now. 2 milliseconds has passed. I need to be doing that right now. So your scheduler is looking at the current time or looking at the global time, and then deciding what's the best operation I need to do first. For example, every task will have a runtime. So every task will require a certain amount of time to run. So, let's say this requires 1 microsecond. Let's say the motor requires 2 microseconds. Then what happens is my scheduler goes, okay, I probably should do the clock first and then the motor next, because I know the clock will take 1 microsecond. So I'll only delay my system by the 1 microsecond. The second thing is the scheduler will also know when to cut something short. So for example, if an operation takes too long, it will cut this operation short. So I've sort of included a Wikipedia diagram because it looks quite nice. This gives you a better idea of what's happening. So for example, P0 has a arrival time of 0. So at the start of the operation, the scheduler will execute P0 here. It knows that P0 will roughly complete around here. That's when P0 will naturally complete. So then P0 will be highest priority until P1 comes along. So let's say P1 comes along at 50 milliseconds or 50, whatever execute time it is. And then in those, P1 will take 170 seconds to complete. So what happens is at around 100, it goes P1 needs to be completed now. So then it moves P2 here and then moves P1 here. And then P1 gets complete, P2 moves up. But what happens is while this operation has happened, you have other tasks that come in. So at 130, P2 comes in. Let's say P2 is the lower priority. And then at 190, P3 comes in. So what happens is your program has to decide on what flow of operation has based on the arrival time and possibly based on the execution time and priority. So for example, it knows P1 must be executed here or must be completed executed by here. So then it blocks, this is what we call a blocking behavior. It just blocks P0 and then moves P0 back. So this could be useful if you want A2 or if you want a robot system to have a very precise timing. So round robin is very good for controlling exactly what's happening at what moment. So often this is good for creating a navigation system or creating a very active sort of schedule for your operations to make sure that there's minimal latency. But the problem with this is that your system might be less stable, because this means that you have to have a very good idea of every scenario that the robot's going to encounter. So before you program this, you need to have a very good idea of what's going to happen with each task. And in real life, you might not have that good idea, or you might not have that perfect understanding of the system's operations. So again, it's not good or bad. It's just more like you have to think about what's the most suitable for your system. So overall, don't take this, as I sort of mentioned before, don't take this as the big full understanding of RTOS. This is more just a single basics of it. So to give you an idea of the basics. If you're interested in it, I recommend reading more about it. So I've included a lot of resources on it. So I'd recommend you guys reading more about it and figure out which one's the most suitable for you and how best to implement this for assignment 2 or the future assignments. Okay, cool. So the rest of this class will basically be for just basically mentoring. So if you guys have questions, feel free to ask questions. And the rest of it is basically just for if you have general questions on the assignments, if you have questions on this class, feel free just to ask us. And you can send Amor or I a message on Teams if you have questions about coding. Cool. Any questions? Yep. So this will be now just sort of open time. So you feel free to either work on the assignment or work on the previous exercise task and let us know how you go.